Welcome to another episode of Unlearning Unlicensed. This is episode 4. In this video series, I am going through RF Elements educational content. It was the advice that they gave to WISPs about how to use their products to help WISPs. And I am going to play their content and then pause to correct the myths, misunderstandings, and misconceptions that RF Elements put out there. Really for self-serving reasons. It was always just so that they could sell more of their antennas and make WISP believe that their products were special. This video is particularly interesting because it's called Increasing Throughput of 5 GHz Fixed Wireless Networks, Increasing Throughput 101 by RF Elements. And this is interesting because it was made, it says 3rd of March 2021. Now, in 2021, RF Elements was on top of their game. It was really peak RF Elements. They won the Product of the Year award for the 3rd time in a row in 2021. It was before Tirana introduced their G1 product, which also helped WISPs with noise in 5 GHz. It was before Ubiquiti Wave product line really took off, which was 60 GHz, which also helped WISP with noise in 5 GHz by being able to provide service to those closer subscribers with direct line of sight using 60 GHz and unload some of those 5 GHz subscribers from the 5 GHz point-to-multipoint network. Also, CBRS was just getting started. So, and Tirana really, of course, boosted the CBRS adoption. But at the time, 2x2 horns were how WISPs scaled up their 5 GHz networks. Also, 6 GHz hadn't emerged yet. So, this seminar from RF Elements was really at the top of RF Elements when they were most influential. And you can see here on this graph from Import Genius, this is 2025 here, 2024, 2023, 2022. There's 2021. This is their total shipments from 2001 or 2006 to 2025. And you can see that 2021, they had the peak of their shipments. They introduced their starter antennas, so their starter horns and their starter dishes, which were their low-cost versions of their products, and but not just low cost, much lower quality. So they took their low-quality antennas and they made them yet even lower quality, and labeled them their starter series. And they flooded the market with these junky antennas in 2021. But here in this video, this is the advice that RF Elements gives to WISPs on how to use their products to scale up their networks, and really handle the noise issues in 5 GHz. So without further ado, here we go.
And the main issue here are the antenna side lobes, which are almost never mentioned when talking about antennas, surprisingly. So high gain, yes, sure, everybody knows about that. The higher it is, the further I can shoot. Beam width.
Okay, yeah. He says high gain. He dismisses it as only being useful for going further distances. That's not true. So the throughput is largely determined by the channel width of it combined with the modulation rate. That determines the speed or capacity or throughput of the wireless link. Now, the modulation rate is determined by the signal to interference and noise ratio. So that's the amount of signal, basically, minus the amount of noise and interference. And with more gain, you can get more signal. But importantly, with more gain, you also can get less noise, because gain describes the amount of focus of the antenna in a specific direction, in the desired direction. So when you focus the signal, that gives you more signal. But also when you focus the signal, you pick up less noise from unintended directions, undesired directions. So gain focuses the signal and it picks up less noise. That's the function of high gain. Very strange that they start this webinar by dismissing gain.
Of course, you want to know how wide of a sector you can get. Maybe front to back ratio, but
okay, I'm going to back up there.
Actually,
so
high gain, yes, sure, everybody knows about
gain.
that. The higher it is, the further I can shoot. Beam width, yes, of course, you want to know how wide of a sector you can get.
Okay, so he says beam width. Of course, you want to know how wide of a sector you can get. Beam width and gain are related. The higher the gain, the more focus, the smaller the beam width. And this is very obvious when you're looking at dish antennas. So a 30 dBi dish in 5 gigahertz will have a beam width of about 6 degrees. Whereas a 36 dBi dish in 5 gigahertz will have a beam width of about 3 to 4 degrees. Now, as you increase the size of the dish, you increase the aperture of the dish, you increase the focus of the signal, and you narrow the beam width. So size, aperture, gain, and beam width are all related. So he just dismissed gain. Now he's dismissing beam width. He's talking about beam width only from the perspective, he says, sector antenna. Of course, you want to understand the coverage area of your sector antenna. I'm going to try to back up here again to get exactly what he says.
The further I can shoot. Beam width, yes, of course, you want to know how wide of a sector you can get.
So he says beam width, you need to understand how wide the sector is. That's true. The beam width determines essentially the coverage area for the sector. But that's not the only purpose of beam width. And in fact, in regards to this topic, beam width is the main reason why horn antennas, they have narrow beam widths, or they can have more narrow beam widths than your traditional sector panel antennas. So your traditional sector panel antennas have 120 degree or 90 degree beam widths. And with those wide beam widths, they're picking up noise from these large sectors. Horn antennas can have 90 degree, 60 degree, 30 degree, 20 degree beam widths. And with these narrower beam widths, they're picking up much less noise. So they're focusing the signal for higher gain, and they're picking up less noise. Interesting that he starts this seminar dismissing gain, dismissing beam width.
Be front to back ratio, but...
And then he dismisses front to back ratio. Now, front to back ratio is the description of how much energy goes in the forward direction versus how much energy goes in the backwards direction, in the back. So that's the front to back ratio. This is the antenna parameter that is used to measure the side lobe performance. And he says front to back ratio doesn't matter, side lobes matter. Well, the front to back ratio is the measurement of the side lobes. And it's important because it's an objective measurement. It's the forward energy divided by the backward energy.
Not so much about the side lobes, so which are the main cause of the problems with noise in unlicensed WISP networks. And WISPs often do try to mitigate the noise of their networks using various shield kits. And if you must use an additional shielding for an antenna to work properly in the first place, then probably it's a good idea to look for a different antenna.
Okay, so that's nonsense. If you have to use shielding to make your antenna work properly, then you should probably look for another antenna. Or you know what? You can use shielding to improve the performance of your existing antennas. That's fine too.
And shield kits like these might improve the front to back ratio a little bit, which is great, right? No, actually, not really. Except the rare case of exactly back-to-back facing antennas. Front-to-back ratio is a useless parameter in terms of.
So he says, except in the rare case of back-to-back antennas, the front-to-back ratio is a useless antenna parameter. That's not the case. So the front-to-back ratio measures the amount of energy in the forward direction versus the amount of energy in the backwards direction. And so if you have this energy going in the backwards direction, then that's going to negatively influence the front to back ratio. And of course, it's always better to focus the signal in the intended direction than it is to have side lobes. This is just a bizarre claim because their whole claim is that side lobes are the problem. But they also want to say that shrouds don't effectively deal with side lobes. And then they show an animation showing shrouds effectively dealing with side lobes. Now, if this dish is co-located with other radios, then reducing these horizontal side lobes, these side lobes coming out directly from the sides, is going to help prevent noise and interference with the other co-located radios. So this shroud is doing its job, and it appears to be doing its job effectively.
Rejection, and the major side lobes are not affected by these shields. All that the shield does is that it rearranges the side lobes. So they point in different direction than without a shield, but they're not suppressed at all, as you can see from this comparison.
So you can see that they are suppressed. You can also see that it's rearranging the side lobes so that they're pointing more forward. Now, if you're on a tower and you've got side lobes and you've got co-located radios here, of course it's helpful to point your side lobes out the front of the antenna, which is then you're going to be picking up noise and interference from further away. And on average, you're going to have less noise and interference, but also that noise and interference is going to be more attenuated because it's further away than the co-located radios on the same tower.
On the left, there is the near field radiation of a typical parabolic dish antenna without the shroud. You see a lot of happening there. So from right to left, there's the main beam, and then as you go off that direction, there is a lot of minor lobes, and those are the side lobes you know very well. While on the right side, you see the same exact antenna, but with the shield, which you can see, or barely see here at the edge, as this horizontal line at the edge of the antenna. And yes, you can see comparing the backs of the antennas, like, okay, the front to back ratio improved, congrats on that. But the rest of the side lobes, as you can see, are still there. Sure, the directions are different, but hell, they're still there, and some are stronger, some are weaker. As I said, they're just rearranged. Nothing really happened to them.
So rearranging the side lobes is exactly the purpose. So yes, it is helpful to point the side lobes in a direction that is not the co-located radios on the same tower. You don't want to send a back lobe to an antenna that's directly behind you. And you don't want your side lobes going vertically up and down, interfering with radios above and below you. You want to send your side lobes out the front of your antenna, again, so that you are attenuating the noise and picking up less co-located noise and interference.
And over the years, the radio vendors have developed their hardware to improve the noise situation through GPS sync, for example, which ensures that the APs within your network transmit and receive at the same time to prevent the self-interference, which is also a huge part of the problem with the noise in general.
Okay, so he does a pretty reasonable job of describing GPS sync there. So with GPS sync, you need to have radios of the same brand and of the same technology, basically the same generation. And you need to set the TDD, the time division duplex settings, so that your uplink and your downlink ratios are the same. So with all of the access points on your tower. So you want to set them all to be 50-50 or 80-20 or 75-25, but you need the uplink and the downlink ratios to be the same. And then you use GPS timing to synchronize the clocks. And then they will all transmit at the same time, and they will all receive at the same time. And this prevents one radio from trying to pick up a signal while another radio is sending a transmission. Because if you have two radios in close proximity, then the transmission is going to overwhelm the received signal, because the received signal is coming from far away. It's very faint. Whereas co-located radios are in very close proximity to each other. So even if they're pointed in different directions, even if they're operating on different channels, because they're so close to each other, the transmission will overwhelm the received signal. It'll swamp it out. And then the radio is going to have that station resend that signal again, because it's not going to be able to differentiate between this radio's transmission and that faint signal coming in from that remote station. So with GPS sync, they all send at the same time and they all receive at the same time, and then you don't have co-located transmissions overwhelming the received signal. But to achieve that, you need to have radios that are all from the same vendor, using the same GPS synchronization technology, and they have to all have the same TDD settings or uplink downlink ratios. But what's wrong about RF Elements is that they say that with their antennas you don't need to spend money on expensive radio solutions. You can just buy their antennas. Well, that's not true. These radios all have something to offer. The GPS sync is necessary for co-located radios, so that you can do A/B channel planning. So with A/B channel planning, you don't have to worry about what your co-located radios, what channel they're operating on, because they're all sending transmissions and receiving transmissions at the same time. You just have to worry about the stations not having overlapping signals. So you don't want channel A here and then channel A here again, because on the edges you'll have stations that are both sectors are able to hear. So you can do A/B channel planning. So you have A, B, and then you can reuse A over here, because this A and that A don't have overlapping coverages. And that's what horn antennas are good for. Their narrow beam widths are good. The signal sharply drops off outside the intended beam width. So a 30-degree horn at 30 degrees has a signal that sharply drops off, and that allows for channel reuse and coverage planning with A/B channel planning, but you need GPS sync. Active filtering filters out of channel interference. So if you're operating on channel A here, and then this radio is operating on channel B, the channel A radio will filter out the noise from channel B. And similarly, channel B will filter out the noise from channel A. But it doesn't get you frequency reuse, because if you have channel A over here, then the filter is not going to filter out the noise from the other channel A radio. So you need GPS sync you need active filtering, but you primarily need active filtering to filter out radio noise that you can't use GPS sync. So if you're co-located on a tower with your competitor, then you need to use active filtering to filter out their unsynchronized transmissions that you're co-located with. And then the horns help with their narrow beam widths, which helps with channel planning and frequency reuse, but it also means that if you have a narrow beam width, you're picking up less noise from the sector. So you're focusing the signal within a narrow sector, and you're picking up less noise and interference from outside the sector. That's how horns help. That's not a replacement to these. It's a complement to all of these. But that's not what RF Elements says.
Or, on the other hand, active filtering, which ensures your radio does not see out of channel signals. And these improvements are efficient, but also costly, and do not really deal with the root cause of the problems with interference, but with its consequences, which is a wrong approach, right? I mean, it's like trying to remove the smoke, but not doing anything with the fire that has caused it.
So he's describing GPS sync, active filtering, 4x4 MIMO, and LTU custom silicon as a wrong approach. It's like dealing with the symptoms, but not with the root cause, which is totally incorrect. GPS sync is the right approach. That is dealing with the root of the problem by synchronizing the transmissions. Active filtering, again, dealing with the root of the problem by filtering out of channel interference. All of these are useful. They all complement each other. There's not one single solution for everything.
Therefore, the first component on the way to increasing the throughput of a wireless network in unlicensed bands is to mitigate the noise. Our solution is different. Now, it deals directly with the source of the noise, not its symptoms. So prevention is much better than the cure. We all know that. And you don't want to just suppress the symptoms, but remove the root of the problems. And RF Elements technology is the prevention.
So that they make two claims. They claim that their horns have no side lobes, and they claim that all of the noise apparently comes from the side lobes, which is nonsense. And then they got another claim that their twist port adapters have zero cable loss, which is also nonsense because underneath this plastic housing there are coaxial cables. So they make two claims, both of them false. But this is how they say that their product helps WISP deals with the root of the noise problem.
Provides efficient noise rejection and mitigation of loss within the radio system itself. And this is achieved through the horn sectors and twist port ecosystem. So the horn sectors deal with the noise efficiently thanks to their zero side lobes radiation pattern. And twist port, on the other hand, is an interface that introduces practically zero loss to the signal delivery from the radio to the antenna. The core issue of traditional patch array sectors are their frequency-dependent side lobes. So they have the side lobes because of the physics of patch array antennas. Simple as that. And these side lobes are an inherent property of the patch arrays as a type of antenna. So the side lobes you see on this radiation pattern, despite being substantially smaller than the main lobe, do decrease the SNR the radio is working with, which cripples overall network throughput and performance.
Okay, so he's partly right. Side lobes, you can pick up noise from your side lobes, but that's not where the majority of the noise comes from for WISPs. The majority of the noise for WISPs comes from inside the coverage area, and sector panel antennas while they do have more side lobes than a horn antenna, the problem for sector panel antennas is primarily their beam widths. So most sector panel antennas are 120 degree beam widths, some are 90 degree beam widths, but these wide beam widths mean that you're picking up noise from an entire sector, an entire 120 degree sector or an entire 90 degree sector. And it's the narrow beam widths of horns that makes them particularly well suited for noisy, unlicensed point-to-multipoint WISP application. So if you have a 30-degree horn sector, it's going to pick up substantially less noise than a 120-degree sector panel antenna. So it's not the side lobes that are the problem here. It's the coverage area. It's simply that with the sectors, you're trying to cover too much. And the horns can have a much more narrow beam width. And so you see that here. So just backing up, here's the sector, and here's the horn. And you can see that this has a more narrow beam width. It's not the supposed side lobes that are the problem here. It's simply the beam width. And there's another problem here with RF Elements presentation. So they are taking a radiation pattern. So this is a radiation pattern on the right, and this is a 3D radiation pattern, and this is a 2D radiation pattern. But they're taking the radiation pattern and they're putting it on a map as if a radiation pattern, an antenna pattern, and a coverage are the same. The problem with this is it gives you the impression that if you have a station right here, then you're going to receive signal. And if you have a station right here, then you're not going to receive signal. That's not what an antenna pattern tells you. An antenna pattern describes how much signal you can expect at any given angle relative to the center of the beam. So it measures signal at various angles. And a 3D antenna pattern does the same thing in 3 dimensions. So, for example, if you get negative 50 dBm RSSI at the center of the beam, if you were to move 15 degrees off from the center of the beam, then you would get the level of signal described by the antenna pattern, maybe negative 6 dB signal for your typical 30-degree sector. But RF Elements is taking 3D antenna patterns here and 2D antenna patterns here and overlaying them on a map as if this was representing a coverage area. That's not the case. But nonetheless, you can see that a narrower beam width antenna, like a horn, is going to pick up less noise than a wide beam width sector panel. And that's how horns help with noise, not with however RF Elements describes it here.
Without generating or receiving any noise through side lobes. Now this effectively isolates your network from the surrounding noise, which in the essence is the essence of dealing with noise in unlicensed WISP networks. Getting rid of the side lobes equals getting rid of noise.
That's not true if the noise is coming from the sector. So if the noise is coming from the sector, which it always is, so how noise comes from the sector is you have Wi-Fi radios, Wi-Fi routers, residential Wi-Fi routers all throughout the sector. You have competing WISP CPEs all throughout the sector, and they're generating noise and interference. It's not the side lobes, it's coming from within the sector. So of course, if you focus the signal, then you're going to be picking up less noise with a more narrow beam width. The other thing that's important about narrow beam widths is that you can divide up a 120 degree sector into 4 smaller 30-degree sectors. And in doing so, you're concentrating the signal, you're reducing the amount of noise and interference that you're going to pick up, that the radio will hear. You are also dividing up the number of stations on the sector, on the access point. So on average, you'll have 1/4 the number of stations. But also, on average, those stations are going to be closer to the center of the beam, where the signals are strongest and the chains are most balanced. So that's how horns help WISPs scale up their networks. Peak RF Elements 2021, they don't describe that. I think they actually believe their own nonsense. I think that they believe what they're saying is true. They just don't know what they're talking about.
And all kinds of parabolic dish antennas used for point-to-point or ACPE application also have significant side lobes, and thanks to which they cover vast areas beyond the main lobe, which is not desired. And this also makes them receive the noise from these areas through the side lobes. As a result of that is, it's similar as with the patch array sectors. It's actually exactly the same. So
No, it's a little bit different, because with the patch array sectors, you're using a patch array sector to provide coverage to an area. With a dish, unless you're using a dish as a sector, typically you're using a dish in a point-to-point application where you have a single source. And what you want to do in a point-to-point application is you want to focus the signal as tightly as you can. You want as much gain as you can get directly at that point, at that source. And he's right that all these side lobes are noise, but he's wrong here because he shows the main lobe as not picking up noise. That's not the case. The main lobe also picks up noise from the main lobe. And it doesn't matter. You want as narrow beam width as possible. You want as much focus specifically at that source in a point-to-point application.
Stable network throughput. This is a radiation pattern of our UltraHorn, a high gain and narrow beam width horn antenna.
So again, these two blue lobes, they are also picking up noise. So these two beams are picking up noise from the entire area that they're operating in. The only signal that matters is the signal right here in the between these 2 points. All of this is picking up extra noise. What you want here is as much gain as possible because you want to concentrate the signal at a single point. And the wide beam width, the low gain of UltraHorn means that it's going to pick up noise from unintended directions, which is directions everywhere except for the single point-to-point radios.
And also UltraHorn has only one main lobe and nothing else. Suppressed noise and maximized throughput.
Not necessarily suppressed noise, as I just described.
So no side lobes equals no problem.
So no side lobes helps, but it doesn't mean no problem if the source of the noise and interference is coming from the main lobe.
Saying an antenna has or doesn't have side lobes is quite vague, and this is
okay. Saying an antenna has or does not have side lobes is quite vague, says RF Elements. This is like I don't know. I don't even know what to say. Saying an antenna has or does not have side lobes is a binary statement. It is either true or it isn't. It doesn't get less vague than that. This is bizarre because it's like RF Elements is saying the opposite of reality and just expects everyone to believe it. And strangely, nobody ever called this out. Have you ever heard of anyone criticizing RF Elements before I started criticizing RF Elements? How did they get away with this? So, yes, saying an antenna has side lobes or does not have side lobes is a binary statement. Beam efficiency, which is what they're about to describe, is subjective. It's the opposite of that.
Where beam efficiency comes to the rescue. It is a measurable variable that quantifies side lobes. In other words, it expresses the amount of side lobes an antenna has numerically. And because it is measurable, it's also does so reliably. So beam efficiency is the ratio of the energy in the main lobe to the total energy an antenna radiates. So the maximum beam efficiency you can achieve is 100%, in which case antenna has 0 side lobes because 100% of the energy it radiates is in the main lobe. The closer to 0 beam efficiency is, the more side lobes an antenna has, meaning more problems for your networks. Here is a radiation pattern of a generic parabolic dish. Its beam efficiency is 40%. This means that 40% of the power the antenna radiates goes into the main lobe. The remaining 60% is in the side lobes, because everything outside the main lobe is a side lobe.
Okay, so they describe beam efficiency as the ratio of energy in the main lobe relative to all the side lobes. And the problem with this, although they have these nice little pretty graphics, is that ends up being a subjective measurement because there's no objective way to determine where the main lobe ends and the side lobes begin. And that all changes depending on the frequency that you're operating at. So oftentimes what you'll have is you'll have a main lobe, and as you change frequencies, you'll start to see side lobes emerge from the main lobe. At what point does it stop being the main lobe and start becoming a side lobe? That's subjective. That's a subjective definition. So who gets to decide when it's part of the main lobe and when it becomes a side lobe? Apparently RF Elements, but this is why it's not, just because it's measurable doesn't mean it's objective. The front to back ratio, by contrast, measures the amount of forward energy relative to the amount of backwards energy. It's the amount of energy in the forward direction versus the amount of energy in the backwards direction. That is measurable, and there's no subjectivity to it. So that's why the front to back ratio is used as an antenna parameter by all antenna manufacturers, whereas RF Elements is the only one to use beam efficiency, and they just made it up for their own purposes so that they could beat up their competitors, as we'll see.
Front to back ratio, for example, only quantifies one side lobe precisely. Yeah, and that's
so this is the crazy thing. Again, it's like opposite day with RF Elements, but every day is opposite day with RF Elements. So no, the front to back ratio is the forward energy relative to the backwards energy. He just said that beam efficiency is the main lobe versus the side lobes, but he's about to confuse the front to back ratio, the main lobe versus the back lobe. That's not how the front to back ratio is measured. It's not the main lobe versus the back lobe. It's the forward energy versus the backward energy. All right, let's let RF Elements continue.
Lobe. But beam efficiency is calculated from full 3D data of the radiation pattern, so making it the most complete measure of side lobes out there. It considers all the side lobes an antenna has. The comparison of antennas in terms of side lobe performance becomes extremely simple with beam efficiency. The higher it is, the better. That's it. An UltraHorn on the left of the slide, you can see, has beam efficiency of 99%. So only 1% of the power it radiates is in the side lobes. A generic dish, on the other hand, has beam efficiency of 40%. So the remaining 60% it radiates is in the side lobes. And clearly 99% is more than 40%. So UltraHorn is way better antenna in terms of noise suppression. And to our knowledge...
Okay, so 99% is better than, what do you say, 40%? Sure, 99% is better than 40%. That doesn't mean it's better at noise suppression. So it depends on where the source of the noise is. Is the source of the noise in the side lobes, or is the source of the noise in the main lobe? And it's quite likely, particularly with point-to-point links, that you're going to pick up a lot of noise from the main lobe.
It's the best antenna on the WISP market in terms of noise suppression. Vast majority of antennas used for sectorial coverage in WISP networks are either patch arrays or horns. And the patch arrays, due to the strong and frequency-dependent side lobes, have beam efficiency values of around 60%, depending on the manufacturer and the quality.
So I just want to point out, this is the reason why RF Elements came up with a beam efficiency antenna parameter, is so that they could beat up their competitors with it. They could assert that their antennas are better. Basically, how that goes is they measure their competitors' antennas, and then they subjectively determine where the main lobe ends and the side lobes begin. But they don't give you they're not showing you their work here. They're just asserting that their competitors have worse beam efficiency. They're not showing you how they got this information. They're not showing you where this data came from. It's mere assertion, but it's also subjective. Obviously, RF Elements has a long history of misrepresenting their products and misrepresenting their competitors' products. But this beam efficiency, it's just worth noticing, only RF Elements uses beam efficiency. There's already antenna parameters that you can use to measure the performance of antennas that are objective, but RF Elements is using a subjective antenna parameter that they made up for the purposes of beating up their competitors. Also notice that when RF Elements fans tell me, David, if you should just focus on your own products, you need to stop talking about RF Elements. They never say this about RF Elements. Go to this video, look at the comments. Where in the comments are people telling RF Elements that if their products are so great, why are they talking about their competitors? Why don't they just let their products stand on their own? RF Elements has always been given a pass on this. They've always been allowed to trash their competitors' products. Notice this is unfair. Notice that this is just assertion. Notice nobody is calling them out.
Of a given design. The RF Elements horns, both symmetrical and asymmetrical, have beam efficiency between 90 and 95%. So you can see actually that there's also other horns in this graph too. And this is to highlight the fact that having a horn antenna does not automatically mean its beam efficiency is high. And the stable and zero side lobe performance is not a given as soon as you have a horn. But we do put a lot of effort into optimizing our antennas, and the results are clearly showing.
So this is interesting because I think that RF Elements probably does optimize their antennas for beam efficiency. And the result of that is that they limit their antenna design choices based on trying to optimize for this fake beam efficiency. IsoHorns doesn't optimize for beam efficiency. We don't optimize to minimize side lobes. We optimize for gain, and we optimize for VSWR and port isolation and front to back ratio. We optimize for real antenna performance parameters. And that's why IsoHorn's antennas beat RF Elements antennas in side-by-side comparisons every single time. But I think RF Elements actually does believe their own nonsense here. And they limit their product based on their own conceptions about how their product should work. And so this beam efficiency, not only are they using it to unfairly beat up their competitors, but they also optimize their antennas for beam efficiency, and in the process they sacrifice other things.